Okay, so we should be looking. You should be now looking at the title page of my presentation, which is about PSC Toolkit, and this is the topic of the presentations that we are going to see this morning. The PSC Toolkit is a project that has a long ancestry, and we started quite some time ago with my work on parallel sparse, on kernels for parallel sparse computations. Then along during the history of the project, we added a number of preconditioner options, and now we have decided to bring all of the various bits and pieces under the same name, which is exactly PSC Toolkit. And in my presentation, I will be dealing with the basics, with the PSBLAS, which is the underlying framework on top of which you have all of the other options. And in the presentation later today, you will hear about the development of specialized preconditioners for which have given good results in the context of the energy applications, both in the context of the wind simulation applications as well as the water table and fluid flow simulations. And then you will get a short demonstration with some exercises. Okay, so this is our logo, and as you can see, there is there are three components. There is PSBLAS, which stands for Parallel Sparse Basic Linear Algebra Subprograms. It's a project that was started under the inspiration of the PBLAS, which are the underlying layer from Scale-up, but specialized for the sparse operations. Then you have the green box, which is a GPU plugin, which I think we are not going to discuss it in detail today because there is not enough time. But just so you know that we do run on GPUs. And then there is AMG4PSBLAS, which is the preconditioner package based on algebraic multigrid with lots of variations and combinations that we will hear about in the later presentation by Pasqua. Okay, so this is the team. The current main core team is myself, Fabio, and Pasqua for PSC Toolkit. And contributions to PSBLAS include all of these other people along the years. And the software is available from GitHub. You have the address, the URL here, and so you can download it freely and you can play with it. And it is also installed on the EoCoE portal which is handled by PSNC, so you can use it as a software as a service, and I presume that Fabio will show you a little bit of that. Okay, so let's see. The basic package, as I said, is called Parallel Sparse BLAS. Which is designed for implementing iterative solvers in parallel. Now, the problem is that solving linear equations in parallel for sparse linear algebra requires an amount of infrastructure which is quite substantial. And it is a lot more than solving dense linear algebra programs because you have to support the discretization mesh, the handling of the discretization mesh. which is what we do. So we do have a number of support functions that are not strictly speaking about computing sparse operations, but they are supporting in the sense that they enable you to build your application. And the main application is still about PDEs. So we have a number of design choices that were made for PDEs. Although there are some other, shall we say, less traditional applications, such as computing the first eigenvector of a graph, which also known as Google, and some other stuff that you can implement with the same kind of kernels. The basic idea is to have the data distribution onto your parallel machine, which is guided by some sort of graph partitioning. We do not force you to use any graph partitioner. You can use any that you like, because there are so many variations and so many ways of doing graph partitioning. Maybe you have your favorite library, your preferred library for doing it. Maybe your problem has some special features such that you can devise a special purpose strategy which works well for your problem, but not necessarily for other problems. So we do try to support all of these variations. And also we do have support for overlap, although overlap mostly comes up in some of the preconditioners that you will hear about later on, especially in the additive Schwarz preconditioners. Obviously, dense linear algebra and sparse linear algebra have seen an enormous amount of work and a number of attempts at standardizing things. And so now we have version 3.8.0 of our library, which is available from the URL that you see here. On the GitHub site, you will find an overall page that contains links to the various components. But there are RPMs available for Fedora and CentOS if you are using those Linux distributions, and also, version 3.7 is already installed on the EoCoE portal. Version 3.8 was released just a couple of weeks ago, so it's still a bit new. And we will discuss some of the new features. Okay, so let's see. This is the library structure. The structure internally uses MPI, and it uses our own implementation of a serial sparse BLAS standard. It does have a parallel interface, and it is usable from either Fortran or C. Most of the implementation is a mixed language, with I should say the majority of code written in Fortran, but also a significant portion written in C, especially in the plugins. So the application can be written in either language, and if you want to install the library yourself, the usual configure, make, install will get you through the basic steps. Okay, so we wanted to this is a recap of why we started with this project, because there were many standards for many ideas for how to write sparse solvers in both serial and parallel mode, and we wanted to make sure to have both attention to performance as well as attention to usability, and trying to ease the job of the developer or the user by providing some support tools that would help you in, for instance, in creating the data structures that you need to implement the basic operations. Basically, we have one very simple interface, and we provide you with a way to delegate building the data structures to the library, and therefore you don't need to delve into the data structures yourself. As I said, when you're dealing with sparse matrices in parallel, essentially what you're doing is you're also handling a discretization mesh which is distributed onto your parallel machine. So these are the basic components of our library. We have some parallel environment handling. We have computational kernels. These ones you could expect very reasonably: sparse matrix dense vector product, sparse triangular system solution. You have vector and vector norms, vector sums, dot products, and the like. But we also have data exchange and update, and we will see that this is the key communication operation during the runtime, the lifetime of the solver. And we have data management, preconditioner setup, and then we have multiple variations on the Krylov subspace solvers that you may wish to choose from. Okay, so let's start first with the parallel environment. Why defining a parallel environment? Well, there are two reasons. The first one is that historically, when we started this project, there were alternatives to MPI. So we wanted to have a unified way of doing things. But there are some advantages. MPI is a very complex piece of software. It is extremely powerful, but also it can be bewildering to the end user. In fact, I remember hearing some of the original developers of the MPI standards saying that they never expected MPI to end up in the hands of the end users. They expected MPI to be used by compiler writers. And yet here we are today with people dealing with MPI. So we chose to get a, shall we call it a simplified version of MPI, a simplified wrappers around MPI that will help you with some of the typical issues that you may find in dealing with MPI. For instance, we make use of the generic interfaces available in the Fortran language to make sure that there can be no type mismatch when you do sends and receives, which is a very, very common mistake from a beginner MPI developer. So the basic operations are to start up a process grid, which is equivalent to setting up your parallel machine environment. Then we have the point-to-point sends and receives, and then we have collective operations. And these are the basic kernels that you can think of in your parallel environment. So each context, which is essentially equivalent to an MPI communicator, will provide you with the virtual parallel machine. So you have an init call, you have an info call, which tells you which role each of the current process is playing within that context. And then you have an exit routine, which will optionally shut down the entire MPI environment. If you put in the optional argument close equal false, then MPI will not be finalized and you can reinitiate your computation in some other way. These are the rules for using these routines. By the way, as you can see, all functions and all subroutines in PSBLAS are prefixed with the PSB underscore characters so that they can be easily identified. If you need to use some of the features of MPI that are not wrapped in our library, you can get the communicator and the rank of the current process, and so it's quite easy to access MPI under the hood. Whenever you create a new context, you are also creating a new communicator, so that the communication within the library happens in a safe space that is cleanly separated from the application side of your the application side of your communication. So this is a hello world, and it's a very simple file, program hello world. You use you include the definition of the library. And you have the context, which is of a derived type, a PSB context type. Then you have some integers, and you call init, you call info to determine who you are. And then if you are the root process, I want you to notice this particular statement here. Whenever you see a symbolic name that is prefixed with PSB underscore and ends with an underscore, it is a constant defined in the library. So PSB root is the default root for operations that require a root process, like broadcasts or things like that. Its default value is 0, obviously. And so in this program, you are printing a welcome message with the version string of the current library. Then you can print the name of the program, and then you print your usual message. You call PSB exit, you stop, and that's the end of your hello world program. So it's a very simple structure. Okay. To use PSBLAS, you really want to use the make file that we defined at install time. If everything goes correctly, you can include that make file into your own main make file, and you can define these rules to get your compilation started. So what about the C interface? Well, the C interface has the following features. First, you can see here this PSBIT. This corresponds to integer PSBIPK. Maybe I should, because integers can come in different lengths. So in PSBLAS, the most common integers are IPK. That refers to local indices. By default, these are 4 bytes. But then there are some indices that can be declared as LPK for long, which can be by default 8 bytes. Therefore, you can handle an index space that is sufficiently large. To these integer types in Fortran, there corresponds the integer types in C. So PSBIT is the usual return value for this routine, and then you have the other interface, which is contained in this include file. All of the PSBLAS routine from the C interface are prefixed with this string here, PSB underscore C underscore, so that you can easily identify them and distinguish them from the basic Fortran interface. Because you do not have generic interfaces in C, you have to add a precision to specify whether you're using an integer, single precision, double precision, or complex variant of something. As an example, the hello world program that we have seen before can be implemented with this simple code, and And well, I don't think you need much more in the way of of description of this one. Okay, and this is again the make file with the variants that you need for the compilation of the C example. Okay, let's now switch to point-to-point communications, sends and receives. Now, as I mentioned, sends and all of the communication routines are implemented with the help of the generic interfaces, which means that you have a single entry point, which is called, for instance, PSB send, for any allowed variation of the data type. It can be an integer, it can be a real, it can be complex, it can be a scalar, it can be an array, whatever. And the compiler at compile time will dispatch the appropriate inner calls. Okay. The destination and the source are obviously the processes, and there are some optional variables that are not very interesting. And obviously, you have to make sure that you match the data size on the sending and the receive process. The semantics of this routine is to have locally blocking sends, which means that the data buffer can be reused as soon as the function has completed, whereas the receive is blocking, which means sorry, the locally blocking send means that you can reuse the data buffer, but that does not necessarily mean that the message has already arrived to the destination. It may be in transit still. Whereas the receive is blocking because it will only complete when the entire message has arrived. Okay, so this is the default communication mechanism. For the collective operations, we have the usual broadcast, sum, absolute maximum, we have scan and exclusive scan. By the way, these two and these arguments are new in version 3.8. So if you are in version 3.7, you don't have the mode and request optional arguments. The data item that you want to communicate can be an integer, a real, complex, can be a scalar, an array. Obviously, it does not make sense to ask for a maximum on complex data, because complex field has no maximum, but you can ask for the absolute maximum value on complex data. So that is okay. The default, the root of the operation has a reasonable default, which is 0 for a broadcast and -1 for the reductions, which means that all of the participating processes get the result. In version 3.8, you can split the collective operation with a start and end calls. And you have a request handle that you have to transfer from the starting call to the end call. Obviously, between those two calls, you should not use the data that was specified in the broadcast, because in the collective operations, because the results will not be reliable. They will only be reliable after a call to a collective end with mode equal collective end. Okay, this can be useful in certain situations. Okay, so what maybe I took it for granted that you all know what a broadcast is, but just in case, a broadcast is semantically equivalent to the operation in which a certain process, which is the root process, executes a series of send operations to all of the other processes, such that at the end of the operation, all processes have a copy of the same data. This is the definition of the semantics of the operation. It does not necessarily mean that this is the actual implementation of the operation, because there are much better algorithms than this one. And because we are delegating the implementation to the MPI collectives, we can be sure that the implementation will be as optimized as the underlying MPI is. Okay. In particular, this operation here will have a cost that is linear in the number of processes. But there are much better alternatives. For instance, for short messages, you can devise an algorithm that will give you a logarithmic cost, meaning that between the start of the operation on the first process and the end of the operation on the last process, you will only take a logarithmic number of time steps based on the latency of to transmit a single message. The C interface requires you to specify the type of data that you're sending around with integer data, single precision data, double precision data, etc. So you have to specify that explicitly. And obviously you have to make sure that you match the various operations on the root process on all of the other processes. The other typical collective is the sum reduce, which is really an example of a reduction operation, which works in this way, or more precisely. The semantics of the sum is equivalent to having the root process execute a series of receives and then summing all the partial contributions into its copy. And if the result is required on all processes, then the root process executes a broadcast at the end, so that all processes have the same result. Again, this is the definition of the semantics, but the implementation will be quite different and it can be a lot more efficient than this. For instance, you can use the reduction to find perhaps the most expensive way to compute the sum of the squares of the first k natural number, which we all know is given by this formula. So there is no point in implementing a parallel program to compute it, and you would only ever find it in an exercise such as this one. But it's a bit of fun. So you can try this. For instance, when doing it with double precision data, because it can get easily out of hand with integer data, and it is using the reduction to compute the sum. Now, there is an easy exercise for the reader, for all of you who are following this tutorial. And there is a mismatch between this code and this formula, and you are invited to find what the mismatch is. If anybody can tell me, I'll be happy to hear it. Or you can think about it and comment later on during the presentation. Okay. So this is related to the parallel environment. minus one very important communication operation that we will discuss shortly after. Let's now talk about computational kernels. So what are the computational kernels? The first and foremost is the sparse matrix by vector product in parallel. Now, this is a depiction of what is going on with with this kernel. You have to acquire the values of B1, B2, and onto this item BP. You multiply by the coefficients on this row, and you contribute to this C entry in the result. Now, the main point is that you are not doing things as they would exactly as they would appear from this slide. And why is this so? Because the matrix is sparse, which means that most of these entries are zero. And we will see shortly what this entails, because this is equivalent to doing a data exchange onto a mesh across the boundaries among subregions of the mesh. We also need a sparse triangular system solution, which is employed in preconditioning operation. And we also have the dot products and norms. So with the usual dot product in the real or complex domain, it works just as you would expect. And then we have the one norm, the two norm, or the infinity norm on the vectors. And we also have the one and the infinity norm on the matrices. Okay, so these are the computational kernels. We also have scaled sums, AXP-like, where basically it's something like y that gets alpha times x plus beta times y, which allows us to implement various operations inside the kernel solvers. And these are the calls to the functions that implement those kernels. You can see the list of the mathematical operations and the kernel that implement it. Notice that for triangular system solution, we are only dealing with a triangular system that is local to a given process. And that is because performing a sparse triangular system solution in parallel is not an efficient proposition. Therefore, we are specifically restricting ourselves to block Jacobi or hybrid Gauss-Seidel type of preconditioners. Okay, so these are the situation where you have a transpose involved. Notice that dealing with the transpose is possible, but it generates an overhead. So it is best to avoid having to use transposition in your kernels. It might be better to employ an explicit transpose of the input matrix, which is something you don't normally do in dense linear algebra, but in this case it could be a useful thing to do, precisely because the balance of the overheads is completely different. These are the C interface to the various functions, and you don't need too much in the way of the description here. The headers are contained into these include files that you can see here, which are specialized for the various variants. And but they are all included by, you can all use them by this single include file, which provides you access to all the functionality. Okay, So there is this version that gives you full access to the optional arguments. This version here for the matrix vector matrix vector product will give you the defaults, but you can have full access to the various options with this function here. And the same thing for the trend or system solution. Now, have we managed to build a coherent system? Well, if you take the conjugate gradient method from the template book or from any of the SIAM journal that publishes these methods, you can see that there is a line-by-line translation into the implementation with these kernels. You can also have as an easy exercise, you can translate this version into the C version for double vectors and matrices. Okay. Data distribution. Now, this is a tricky issue because doing data distribution is equivalent to handling graphs on a distributed machine. The guiding principle is that you have an index space which corresponds to the physical domain that you're trying to solve, and each process is responsible for one of the indices, which means that that process will compute all of the updates to that to the variable corresponding to that particular index. So each index has a home process which holds the authoritative value for the vector entries. And on each process, you also have a set of resident indices that will have a local numbering, although there also is a global numbering, and therefore there is a need for a map between global and local indices. Okay? Which contains a certain amount of redundancy. Now, the data distribution is equivalent to a graph partition problem because a partition of a mesh is equivalent to a partition of a graph, which is equivalent to a partition of the rows of the matrices if you make each row of the matrix correspond to a node in the graph, which corresponds to a node in the mesh. Now, obviously, finding the optimal decomposition is a graph partitioning problem, which is NP-complete. Therefore, there are all sorts of heuristics for doing this efficiently. And that's the reason why we don't force any particular strategy for doing things. But we can rely on the isomorphism between the sparse matrix pattern and the graph. Okay, and let me briefly switch to the next important thing, which is the communication descriptor, which keeps track of the parallel machine, keeps track of the discretization topology, and it stores the map between global and local indices. And it contains all the data necessary to implement arguably the most important collective communication, which is in the most recent version of the MPI standard, it is called a persistent neighbor all-to-all variable communication. In the literature, it's often called a halo data exchange or a ghost cell update. Let's look at what it looks like. This is the problem. This is a very simple discretization mesh with finite differences, and you have this region has been assigned to processor P1, and this region has been assigned to processor to process P0. However, if you are dealing with the finite difference discretization, if you are dealing with this node here, you require the entries in this, and this, north, south, east, and west. But if you move to this particular node, to this particular node here, if you're going north, you will find that you need the value of a variable which is not local. So you have to retrieve this value. And by the same token, processor P1 will need to retrieve the value of the variable associated with this one. Okay, so you will need a so-called halo data exchange, which is what exactly happens with the call to BSB halo, so that on process 0 you get a fresh copy of the data associated with the global indices from 33 to 40, and on process 1 you get a fresh copy of the values associated with global indices 25 to 32. Okay, so this is the single most important call, and it's also implied by the sparse matrix by vector product. So when you're executing a matrix vector product, you're implicitly executing this operation here. How do you build a sparse matrix? Well, you have coordinate storage, in which you simply store each element with its row and column indices. Or you can have compressed storage by rows, where you are arranging the column indices, you sort them by rows, and then you store only pointers to the starts of the rows. And there are umpteenth other storage formats. If we wanted to tie ourselves to one of those storage formats, we could have done it, but we don't want it, because we want to be able to change in response to machine changes, because what works well on a given machine, for instance, on a normal vanilla Intel CPU, does not necessarily work well on an SSE vector unit, or on a GPU, on an NVIDIA GPU, or on an AMD GPU. So we want to change that. We also want to change at runtime, because what is a good data structure for certain operations may not be as good for other operations. And we also want to switch at runtime, and we also would like to switch among different formats that we did not know when we wrote the original code. So how do we do that? Well, we have to use design patterns, and for the computer science oriented people among you, you are invited to look at those two papers, where you will see the use of these for the design patterns to achieve exactly that result. The overall idea is that we have a data structure that is able to change dynamically at runtime, which also means that we can have heterogeneous computing. We are not tied to using the same data structure on all processes. We can switch from one data structure to the next, depending on whether we are dealing with other stuff. And of course, this is also very useful in the context of the GPUs, where you have specialized data structures, which is included in the PSBLAS extension plugin. And you can see here that the sparse matrix vector performance on the Volta is incredibly better than on normal CPUs. But we are not going to discuss GPUs any further in this presentation. So very briefly, how do we set up a sparse matrix? The first step is to design an association between the index space and the various processes, which can range from a simple one to the more sophisticated one. I think the best one is the following. Let's see. Assign a no, not this one, this one. Build a list of the indices that are assigned to a certain given process, and you initialize the descriptor. There is no requirement for the indices to be contiguous, they do not need to be ordered. The size need not be uniform across the various processes, so you have maximum freedom. Okay. After that, you have this mapping, which is not complete. To get the complete mapping, you have to describe the mesh topology, which you can do explicitly from a graph or implicitly while building a sparse matrix. Because as you remember, the pattern of the sparse matrix is isomorphic to the graph of the discretization mesh. So let's skip this one and go to the allocation of the sparse matrix that will take these optional arguments. And again, these two optional arguments are used in a new way in version 3.8. The first optional argument will give you, the NLZ will give an estimate of the local size. The duplication and build mode will allow you to specify whether the entries that you're putting locally should really end up onto other processes. Now, this is useful for finite element codes, which often progress element by element, and it was decided in the initial meeting of the linear algebra community within the EoCoE project that all software provided by the project should provide this functionality. So with version 3.8, we now have full support for this, which means that what you're doing is a loop like this. If I have this index, I can give my contribution and I can insert it into the matrix. Notice that here I'm describing the entries of the matrix with a simple index, row index, a column index value set of triples, which has nothing to do with the final format, which will be created at this time, where I can specify either a string argument or a mode argument, which will control what sort of data storage I'm really interested in. And notice that these arguments can change from one process to the next, so I can handle heterogeneous computing. Like, for instance, I can use multiple GPUs, and and the mode argument is all that is needed to make a good use of that. Okay, we are already at 5 minutes from the end of the official end. Julianne, how much longer do we have?
Well, if you want to keep in line with the program, let's say that it would be nice if you could wrap up in the next like 10 to 15 minutes. Yeah,
that's certainly doable. So I will go a little bit over the 10 a.m. mark, but not by much.
Absolutely, thank you, Salvatore.
Okay. So there are other specialized usages, but these are not too interesting for a novice. Suffice it to know that it's possible to clone and reuse an existing matrix pattern, which is a useful thing because you might have different matrices onto the same discretization mesh, and obviously you don't want to do things again. The same code structure for the vectors that you are using. Again, you are doing the insertion and the assembly. And these are the C interfaces for achieving the exact same result for all of the various types, single, double, complex, integer, whatever. There are some rules of precedence about all of these calls, so you can read the rules here, and they are very clearly specified in the manual that you can find on in the software distribution. And so you have a general application structure which goes like this. You first allocate a descriptor, then you loop into the descriptor, you insert the description of the discretization mesh, and then you build your matrix. You can also mix some of the operations together in this other slightly different application structure. Okay. a couple of utility routines in case you need to convert from global to local indices. That's perfectly fine. And you can control whether you're including the halo or not. Data query. Obviously, you want to query the number of global and local entries in your matrix, and also the same thing with the sparse matrix structure. So you have the communication descriptor and you have the sparse matrix. By the way, the percent sign in the Fortran language separates the object from its components, in this particular case, from the methods that you're invoking on them. So this will give you the the various bits that you need, and also you have the size of in bytes as you might expect. There are some utility routines for reading data to and from file. They are not recommended, because if you read from file, you are implicitly generating a serial bottleneck, but they can be useful for debugging purposes, for testing purposes. So they are there if you need them. And now let's go to the real deal, the preconditional iterations. And this is our preconditional iteration method in its full glory. So you invoke PSB Krylov, where you can use any of the supported Krylov subspace methods, including BiCGStub, BiCG, CGS, RGMRes, BiCGStub L, CG, flexible CG, whatever. The default is not CG because we currently, because CG is supposed to work on symmetric positive definite matrices, and this is a feature that is not easy, that should be really guaranteed by the user, so it should be given the choice to the user. BiCGStub works with general matrices, even those that do not have a symmetric sparsity pattern, so it's really okay. Notice that if you have a quote normal discretization mesh, you would expect the sparsity pattern to be symmetric. Now, so the first argument is the choice of method. The second argument is the matrix. The third argument is the preconditioner. The fourth argument is the right-hand side. The fifth argument is on input, the initial guess, on output, the solution, if at all possible, then the requested tolerance and everything else. On output, you can get you can also specify a maximum number of iterations, and you get back the number of iterations to convergence together with an estimate of the error on exit. Okay, these are the description of the various choices that you have available. By the way, you have the various stopping criteria, which are critical to define a good iteration. Also, please notice that having a good initial guess can change dramatically the number of iterations to convergence. These are the C variants. The C variants with the basic interface, and also we do have a structure that contains the solver options, which is initialized to default solver option, but you can change them to your heart's content. So it's very easy to get the various combinations that we were discussing before. The preconditioners, the preconditioner is an encapsulated type. You init, you build the preconditioner, and then you apply it inside the iterative method. The basic library contains a basic, very, very basic definition of these preconditioners, like no preconditioning and diagonal scaling, and a simple block Jacobi with incomplete factorization. I am not going to discuss preconditioners in more details because they are the subject of the sister library AMG4PSBLAS, where you have many more variants of preconditioners, a lot more sophisticated than this ones. And you will hear all about them in the next lecture. Here it is. Okay, so if you you can obviously try our test programs, but you can also the test programs can come in two variants. One that reads the input matrix from file, and the other that generates a partial differential equation in three-dimensional with Dirichlet boundary conditions, and you can change the kind of function that you are generating by playing around with the A1, A2, A3, and B1, 2, 3 functions. So you can easily generate Poisson problem, a Laplace problem, or a convection diffusion problem. You can play around with lots of stuff. These programs are installed on the portal, so you can also play with them through the portal. And finally, and we are roughly 5 minutes over time, so I hope that everybody is happy about this. The bibliography, so the original stuff is from these papers here. The inspiration came from the first two papers, and then you have the basic the paper describing version 1.0, which came out a long time ago, and then the object-oriented techniques with the design patterns that I was discussing came out in 2012, and it was updated in 2014 when GPUs came around. For GPUs, you may want to look at our review of matrix vector multiplication on GPUs, and then the first iteration of the domain decomposition packages was presented in 2010, but the current iteration, which is AMG4PSBLAS, will be presented in the next lecture. And I think that I've gone through all of the material that I had. If there are any questions, I will be happy to answer to the best of my knowledge.
Thank you very much, Salvatore. This was, I think, quite clear and synthetic. Since there doesn't seem to be any question at the moment, I suggest we move on to the second presentation of this morning.
Okay, I will stick around, and you can ask me later on if you want.
Yeah, absolutely.
Okay, thank you very much.
Thank you.
Bye-bye.
Okay, Pasqua, you're on.
Hi, yeah.
Hello.
Hello, Julian.
Okay.
How are you?
Good, good. We can see you. You should be able to share your screen by default.
Yeah. Could you see my screen?
Yes, absolutely.
Okay. I go to the full presentation. Is it fine?
Yes, it is. You can go right ahead.
Good. Oh, good morning and welcome to everybody to this second session of our tutorial on scalable linear solver for EoCoE. This is the second part of the training activities on the PSC Toolkit libraries. And I will focus on parallel preconditioner built on the top of the PSBLAS kernels thus presented by Salvatore. The intent of the presentation is to introduce you to the language and the main feature of algebraic multi-grid preconditioners, so that you can better understand the functionalities of our libraries, and also the example available on the portal that will be discussed in the hands-on session of my colleague Fabio just later on. So let me remind that the team working on the preconditioner package, we named AMG4PSBLAS, currently include me, Fabio, and Salvatore. And the activities started some years ago and involved some other collaborators in the past, of course. However, the feature of the current features of the package are being constantly updated during the EoCoE project, with the main aim of efficient exploitation of near future parallel computers working at the exascale. Then many new pieces have been added to the original library, having in mind the scalability issue. And the main reference is this paper published on Science Journal Scientific Computing last year. So main motivation of our works comes from the needs of the EoCoE project, but more generally from the needs of challenging applications in computational and data science. Solving a large and sparse linear systems is a core task in many modern applications. Many times the matrix is asymmetric and a positive definite and very sparse, so that only a small number of non-zero entries are in the matrix row. Another key issue is the size of the system. Indeed, generally in the current applications, we need to solve linear systems including more than 10 billion of unknowns. For example, in the numerical simulation of high resolution models for hydrology studies in EoCoE required to solve systems with more than 100 billion of unknown, and there is a clear tendency to increase this size to prepare, of course, scientific application for the exascale ecosystem. On the other hand, also application in data science, for example, in sparse graph spectral clustering also requires solution of very large linear systems where the size depends on the number of the data, and the demands for memory and the need for short solution time require the use of supercomputers. As I already said, the sparsity of the matrix is a main feature, as already discussed by Salvatore too. And a definition of a sparse matrix that we like to mention is to James Wilkinson, the mathematician that is one of the founders of modern numerical analysis, and he defines a sparse matrix as a matrix having so many zeros entries that is worth taking advantage of this feature for computational purposes. The methods of choice for solving this type, for solving the system associated to sparse matrices are Krylov subspace methods. They don't modify the original matrix so that we can take advantage by using compressed Sora scheme and the basic computational kernels in the basic computational kernel in these type of methods is a matrix vector product whose efficient implementation can be obtained on modern architecture. The archetype of the Krylov class method is the conjugate gradient, whose convergence rate depends on the so-called condition number of the system. That is the ratio between the largest and the smallest matrix eigenvalue. The smaller the condition number, the faster is the convergence of the conjugate gradient. Therefore, in general, the method is applied to the so-called preconditioned version of the system. That is, it applies to a system equivalent to the original one, which has a smaller condition number. I apologize for the expert in the audience, but I would like to emphasize that the choice of operator B, that is another sparse matrix which we name the preconditioner, is a key issue. I show here a simple picture of the relative error in the application of the conjugate gradient to a small system coming from solving the Poisson equation in 2 dimensions on the unit square coupled with the Dirichlet boundary conditions. We discretize this problem by using a simple fine difference scheme on a discretization mesh with 15 mesh points in each direction. In this case, the condition number is about 10 to 3, and we can observe that after 60 iteration of the method, we can obtain 3 digits of accuracy on the solution. The same is obtained with the preconditioner method only in 20 iteration of the method. So if we apply the conjugate gradient method to a preconditioned system with only 1 order of magnitude less of the original system, we have an interesting gain in the solution. So to better present our package of preconditioner, I need to remind main features of the multigrid method. Multigrid are very efficient iterative methods for solving large and sparse linear systems. They derive their efficiency by a recursive application of a 2-grid process, which consists of some smoother iteration and a coarse grid correction. The smoother iterations are generally based on a simple relaxation method, such as the EoCoE or the Gauss-Seidel method, while the coarse grid correction consists in the solution of an approximate, consisting the approximate solution of the residual equation on a coarser space. That is solving a linear system of smaller size. Then the obtained solution is transferred back to the fine tree, and the solution, the fine solution, can be corrected by using some other smoother iteration. The main idea is that highly oscillatory components of the error are damped at the fine level by a smoother. Then the smooth error components, which are not reduced at the fine level, can be damped at the coarser level, where they become more oscillatory. The algebraic multigrid methods are an algebraic version of the original multigrid methods, which originated in the context of the solution of a partial differential equation, where geometry and grids are available. We focus on the extension of multigrid methods designed for more general systems, also coming from non-PV problems. They are called algebraic multigrid since they only relies on matrix entries to set up the method. That is to choose the coarsest space of unknowns from the fine one and to set the prolongators and the restriction operator. A key issue in to obtain good convergence algebraic multigrid method, which emulated the geometric multigrid methods, is that the error components, which are not well reduced by the relaxation method at fine level, and which we name algebraic smoothness of the problem, are well represented at the coarser level, applying a principle of complementarity between fine relaxation and coarse correction. This happens when these errors are well approximated by vectors in the range of the prolongator operator. Therefore, at the end, the key problem of efficient algebraic multigrid is to find the best prolongator for a given smoother, for a given relaxation method. We have to say that having a scalable precondition, which can be promising for exascale computing, imposes some stringent requirements for the possible methods. The ideal precondition is such that the precondition matrix has a condition number small and hopefully the value is independent of the problem size. These results in a most constant number of iterations of the Krylov solvers while the problem size increases. Furthermore, the cost of the application of the precondition should be linear in the problem size, in the sense that it should be optimal also from the point of view of the computational complexity, both in terms of flops and in terms of memory footprint. And last but not least, it should be composed of local operations, reducing data communication among parallel processes in a parallel setting, and leading to a parallel performance which could be linearly increasing for increasing number of parallel cores. Let me present some multigrid performance parameters which are which can be seen as guidelines to write, to design efficient parallel algebraic multigrid methods. Main parameter used as a performance measure include the conversion rate, of course, which affects the number of iterations of the solver, the operator complexity, which is the number of non-zero of the system matrix and affects the computational complexity. And we have to say that both convergence factor and operator complexity need to be considered when we define the coarsening process and the interpolation procedures, since they affect each other in the sense that increasing computational complexity improve generally the performance of the method, but the small complexity lead to a degradation in convergence. So only the user can decide what is the priority for his application. Finally, we have the stencil size, that is the average number of non-zero entries per row of the coarse matrices generated by the method. It affects computation and communication in basic sparse matrix operations for the setup and for the application of the preconditioner. A small stencil size is desirable, of course. However, also in this case, small stencils of the coarser matrices has to be balanced with the convergence properties of the final method. And indeed, the challenge for multi-grid methods on supercomputers is turning an efficient serial algorithm into a robust and scalable parallel algorithm software. Good numerical properties have to be preserved when making algorithmic changes needed for parallelism. This task is non-trivial and affects all aspects of the setup and of the application of the preconditioner. As in more general cases, we have to obtain the best performance at the single processor level, at the single node level, and also reduce the impact of data communication in a parallel setting. On the other hand, we should preserve robustness in terms of convergence properties of the methods on more general problems, and flexibility in parameter setting for wide applicability in terms of problems and also in terms of a parallel architecture and configuration. Some other issues come from efficient use in time-dependent and non-linear problems, such as that some of the application of the EoCoE project. Finally, from the point of view of the application developer, we also need to take into account easy of use and of interfacing with legacy codes. Then high-level users interface is also an important aspect. Multi-grid preconditioner have some optimality features in many cases, such as for systems coming from scalar elliptic partial differential equations. However, we have to say that an optimal preconditioner from the theoretical point of view is not always the fastest preconditioner on parallel machine. So let me go inside to our choices for implementing a modern package based on algebraic multi-grid methods. Our package is a software development project started many years ago. The first release of the package provided multi-level additive and hybrid Schwarz preconditioner, as well as one-level additive Schwarz preconditioner. During the EoCoE project, we extended the library, first of all, to prepare it to run at extreme scale. For example, we use long integers needed to deal with matrices with more than 2 billion of unknowns in an efficient way. And we also implemented the more general algebraic multi-grid than multi-level Schwarz. The package employs an object-oriented design in Fortran, and it is a layered software architecture where at the bottom level we have PSBLAS to manage parallel basic linear algebra computations. We try to apply a clear separation between users' interface and the implementation of the methods. And we also separated, for example, users' interface for setup of the preconditioner of the smoother and solvers at each level. These design choices are inherited by the PSBLAS strategy approach and were motivated by the needs of flexibility and modularity oriented to immediate extensions and software reuse. A first kernel of the package is already available for GPU accelerator, and work for complete setup of the preconditioners on GPU is a work in progress in the EoCoE project and also in some other European projects. Let me go inside the algorithms and library functionalities. The procedure to set up an algebraic multigrid requires the setup of a convergent iterative solver that is the smoother, the setup of a coarser vector space from the fine one, and the setup of the prolongation to move from the coarse to the fine space. And finally, the computation of the coarser matrix by a standard Galerkin type of sparse matrix product. In our package, we rely on a so-called aggregation strategy to group the unknowns into the disjoint set of aggregates. Each one corresponds to one coarse unknown. This is the main strategy for coursing. We aggregate the fine unknowns in groups. For example, we can see in this picture an example based on the Poisson type system. We aggregate the fine 9 unknowns in different groups having different colors in some way related to the properties of the matrices and in order to have an efficient method, of course. A standard way to build the prolongation in this approach is to set up a piecewise constant operator which projects on the aggregates the components on an algebraic smooth vector. A widely used approach named smoothed aggregation and available in our package apply one step of a weighted Jacobi method to this prolongator in order to improve convergence of the resulting algebraic method. This is one of the first approach of aggregation scheme with the very good convergence properties in the case of a scalar elliptic partial differential equation. Current version of our preconditioner can be obtained by a different combination of many methods and software modules. In red, I wrote the functionalities which are already available to run on cluster of GPUs in a hybrid programming model. For setup of the application, which is currently available only for CPUs, we have two different approaches. A parallel decoupled version of the well-known smoothed or just mentioned smoothed aggregation algorithm, and also a new coarsening we developed in the last years, which relies on the concepts and principles of compatible relaxation and weighted matching algorithms. In order to have flexibility in the courses solved, our multi-level hierarchy can deal with a courses matrix which can be replicated on all the parallel processes for sequential courses solvers or distributed among the processors for a distributed solution of the courses system. For the solve phase, we can choose different type of standard multi-grid cycles, such as B cycle, W cycle, and a form of K cycle that is a generalization of a double cycle where the coarser level systems are solved by some iteration of a EoCoE solver. They include many versions of inexact block Jacobi and additive Sparse methods, which can exploit on blocks also some approximate inverse modules available for GPUs. And at the coarser level, we can use all the available smoother as solvers, and also some direct methods from some third-party libraries. In the current version of the package, we also have the possibility to apply iterative EoCoE solvers at the coarsest level in a recursive way. Let me rapidly give some details on the available coursing in order to better understand the functionality of the package. I start from the coupled smoothed aggregation. When we work in a parallel setting, we have to apply the aggregation scheme in parallel. So we can use a so-called decoupled parallel aggregation, where the same algorithm is applied to the different blocks of the matrices which are distributed among the parallel processes. Therefore, in this way, each process applies the same aggregation algorithms which couples the unknown on the base of a measure of strength of connection among the unknowns, only to its own block of the matrix, without considering the connections and interaction among unknowns which are on different processes. In this way, the aggregation scheme is, of course, embarrassingly parallel, since it doesn't require any communication among processes, but generally produce non-uniform aggregates due to the so-called Gauss boundaries among the submatrices assigned to the different processes. However, it is demonstrated in the literature that this approach can give good convergence results, at least for moderate number of parallel cores on classic systems coming from scalar elliptic partial differential equations. The use of more sophisticated coarsening, which can be promising for a larger number of cores and larger number of unknowns facing the exascale challenge, is needed, and during the EoCoE project, we developed a new method for preparing the package to run at extreme scale. This new method relies on the interaction between the concept of a compatible relaxation and some properties of a maximum weight matching in graphs, in undirected graphs. We named this new coarsening based on compatible weighted matching. In this slide, I use the C-match acronym. The method is a recursive application of a two-level hierarchical method, which exploits results for a general theory for coarsening without using any a priori knowledge of a matrix origin and the smooth vectors character. In particular, we propose a two-level hierarchical method which exploits a decomposition, an orthogonal decomposition of the fine vector space. the fine vector space is indeed decomposed as a direct sum of two orthogonal subspaces, a coarse space and a complementary space corresponding to the ranges of two different prolongator operators. Starting from this decomposition, a block form of the original matrix can be easily obtained. And in this block form, we can identify a coarse matrix and a complementary coarse matrix corresponding to the ranges of these two different operators and to the projection of the original matrix on the two different subspaces. A general convergent theory recently developed indicates that this type of subspace decomposition defines a good quality coarse matrix AC if the convergence of a relaxation method applied on the complementary matrix AF is very fast. This result was already guessed by Algebrandt when in some papers they claimed that a coarse space is good if a corresponding compatible relaxation, that is a relaxation keeping invariant the coarse variables, is very fast. Starting from the above principles, we propose to define a coarsening scheme based on aggregation of unknowns whose aggregates are built by a suitable weighted matching in the adjacency graph of the original matrix, so that the matrix AF is as diagonally dominant as possible. In such a way, a simple relaxation method such as Jacobi or Gauss-Seidel applied to AF is very fast. Okay, so the interaction between sparse linear algebra and combinatorial analysis has a long history and finds its basis in the representation of sparse matrices in terms of the associated adjacency graph. Starting from the undirected graph associated to our fine matrix, we consider the following real matrix, which we named AT, and can be considered as weight matrix for the graph. In this setting, a matching in G is a subset of the age set, which does include adjacent ages. That is, any two ages doesn't share a vertex. We call a maximum weight matching in this setting a matching which maximizes the sum of its weight. And starting from a maximum weight matching, we split the original matrix index set in the subset of matched vertices and possible synchrotons due to possible unmatched nodes. Finally, we can summarize the coarsening algorithm, which can be referred as a compatible matching based algorithm. Starting with the given system matrix and the given smooth vector, we apply a pairwise aggregation based on parallel maximum weighted matching and build the intergrid operator by simple projection of the smooth vectors on the aggregates, and then compute the coarse matrices with the standard Galerkin product. At each new level, the vector W is restricted from fine level to the coarser one, and the process can be applied in a recursive way until a maximum number of levels is reached or a fixed size coarse system is obtained. We have said that more aggressive coarsening than pairwise aggregation can be applied in order to reduce complexity and memory requirements. And we can combine to this aim multiple steps of the basic aggregation. For example, we can multiplicate two consecutive prolongators corresponding to pairwise aggregation to get aggregates of sites of at most 4. Of course, we can do this procedure by using more than 2 consecutive prolongators by enlarging the size of the aggregates for each new level. Main computational kernels in this algorithm are almost all contained in the PSBLAS functionalities. Indeed, you can recognize here the matrix, and matrix vector multiplications that are already implemented in PSBLAS. The only one kernel that we didn't have in PSBLAS is an efficient parallel implementation of the maximum weight matching for setup of the aggregation. So, to this aim, we consider some libraries available, freely available in the context of the theory of weighted matching. And algorithms for optimal matchings are very expensive. Indeed, they have superlinear complexity and are intrinsically sequential. Therefore, we decide to relax the request on optimality and looks for near optimal solutions. To this aim, we consider approximation algorithms which guarantee the quality of the computer matching. In particular, they are able to find in linear time a matching whose total weight is at least the half of the optimal weight. Parallel implementation of some of these algorithms are available in Matchbox-P software framework. We get an efficient parallel implementation of a half approximate matching first proposed by Praise from Matchbox-P and integrated it in our AMG4PSBLAS data. Main advantages of our new parallel coarsening with respect to all the currently available aggregation scheme are that it is a completely automatic procedure which is independent of any heuristics or a priori information on the matrix and especially on the near kernel of the system. On the other hand, our coupled parallel implementation produce well-balanced coarse matrices among parallel processes, and there is no need of special treatment for process boundary unknowns. Finally, we can say that we can apply the coarsening procedure in a flexible way by considering aggregates of sites of aggregates of almost arbitrary dimension, and we can improve the convergence of standard V cycle, that is the cheaper cycle which we want to use in a parallel setting, by smoothing the matching based prolongator as in classical smoothed aggregation. In this case, suitable choices in the sites of aggregates allow to obtain a good trade-off between the convergence of the final preconditions and computational complexity. So let me focus at the end on our choice of smoothers. A good smoother in algebraic multigrid is the Gauss-Seidel relaxation method. This is well known, but you know that Gauss-Seidel is based on the splitting of the system matrix, and at each iteration it requires the inversion of a triangular matrix, which is an intrinsically sequential algorithm. Therefore, we studied method to reduce data dependence and exposing more parallelism. These are different versions of inexact Jacobi block Jacobi methods, which include the so-called hybrid Gauss-Seidel, which is a form of the Gauss-Seidel algorithm introduced in the Hyper library, that is the state of the heart of the algebraic multigrid software libraries. In this setting, Gauss-Seidel algorithm is applied as the standard Gauss-Seidel within the local row block assigned to each process, while it is applied as Jacobi across the blocks in different processes. The standard Jacobi method can be seen, of course, as a particular version of hybrid Gauss-Seidel. We also have the Helen 1 versions of Jacobi and the hybrid Gauss-Seidel. In this case, these are more robust version of the previous one. Indeed, starting from the usual splitting of the local matrix block, we can define a local smoother by adding to the local Gauss-Seidel smoother a diagonal weight obtained by the L1 norm of each row, so that the final smoother has the following diagonal block form. And in the case of in this case, usually the iterative method is more robust than the standard version. On the blocks of this type of hybrid block Jacobi methods, we can also apply some version of approximate inverses that are supported in our software framework, in particular in the PSBLAS X components. And these kernels are very good, for example, on GPU accelerator, as they only rely on sparse matrix vector multiplication. Okay, let's go to some results. We test the scalability of our software framework on the standard Laplace equation on unit cube by applying the Euclid boundary condition. The equation was discretized by the usual 7-point fine difference scheme on a Cartesian grid, which was uniformly refined in order to have systems of increasing size. The resulting linear systems are solved by a flexible version of the conjugate gradient method just mentioned by Salvatore, and coupled with the Krylov-based cycle with two linear iteration when unsmoothed aggregation is applied. Then we also use the coarsening based on weighted matching coupled with smoothed prolongator. In this case, a cycle was applied in solver phase. In both cases, we applied the coarsening for having final aggregates of size at most 8. For comparison aims, of course, we also report results obtained by the already available decoupled classic smoothed aggregation scheme inherited by the old versions of the library. And we stop the coarsening for both coarsening scheme when the size of the coarsest matrix is not larger than a fixed size. That is the default the default parameter of the library. In our test, we considered as a smoother the hybrid forward-backward Gauss-Seidel method when we ran on CPU. And we solved the courses systems by using parallel conjugate gradient, preconditioned with block Jacobi and a version of incomplete LU factorization on the blocks. I will show some results obtained on Finite. This is one of the European supercomputer available, operated by the Swiss Supercomputing Center and available through PRAs. And compare our preconditioner with the hybrid that maybe you know is a software project, a software development project of the Livermore, of the Lawrence Livermore National Laboratory. For our aims, we choose 3 different course names showing different complexity and scalability features as recommended in the best practice of hybrid. And we apply the hierarchies as a V-cycle with the same choice of a smoother as in our preconditioners. The 3 different coarsening and the 3 different preconditioners we obtained were named FALGU, HMIS, and HMIS1. So we did weak scalability analysis of course by using a grid with the fixed sites per process, so that the local matrix has 256,000 unknowns per process. I show you results using up to 27,000 cores, leading to a global matrix size of more than 2 billion. We can see that our new coarsening produce a good quality precondition, which shows a very small increase in the number of iterations by increasing the number of cores, of parallel cores, and number of unknowns. We can see that in the case of K-cycle coupled with unsmoothed aggregation, as also in the case of V-cycle with smooth aggregation, we have similar results with the FALGU scheme available in hybrid. Indeed, we can see that the number of unknowns is very similar to the FALGU scheme where we use the new coarsening. The behavior is different for the uncoupled old methods available, in our library, where we can see, as expected, a large increase in the number of iterations for the increasing number of cores. These a similar behavior than the decoupled approach is obtained by HMIS and HMIS1 in hybrid. If we look at the operator complexity of the different preconditions which measure the computational complexity of the schemes, we can see that our new coarsening, when coupled with unsmoothed aggregation, obtained a very small operator complexity, which is just over 1 for each number of cores, and this results in a very small memory footprint and a very small computational complexity. It is comparable with the HMIS1, and while when smooth aggregation is used with our new coarsening, we obtained a small increase of complexity, still remaining under 2. On the contrary, the FALGU and the HV coarsening procedure produce very expensive hierarchies with large memory footprint. This behavior is confirmed in the execution time of the solve phase, where we see that our new preconditioner, that is the sign line, obtained very small execution times. It is best execution times for increasing core. It is smaller than all the high preconditioner, while the larger times are required by the high preconditioner based on H-means due to its large operator complexity, which does prevent a significant increase in the number of iterations. Let me observe that when we analyze weak scaling, as in this case, we would like to see some flat lines. And this is not the case in this type of a problem, which are memory and communication bound due to the sparsity of the matrices. And usually we see a slowly increasing lines. We don't see ideal flat lines, but we can see that in our preconditioner, the time increase is small, is low, and we outperform similar reference methods. Let me give a look also at the time for setup of the preconditioner. We see that the coarsening based on weighted matching is comparable with the FALGU coarsening in Ivory in the case of the smoother prolongators, while in the case of smoother prolongators, the parallel matching is increasing in the time, since the increasing in the number of matrix multiplication produce this increase in the setup time. Anyway, if we take into account the large reduction in memory footprint and in solve time, we can say that our preconditioners are very effective. Indeed, we have to consider that the small increase in the setup times are usually well tolerated in time-dependent and in nonlinear application, when the same preconditioner can be applied several times during the different steps. So here I show some results obtaining going up to 27,000 of NPI cores for increasing mesh size per core, up to 10 billions of unknowns. In the same picture, you can see also some lines related to the use of GPUs up to 2014 GPUs. Let me observe that we are solving a system with a size that is 10 times more than using one GPU, with an execution time that is only 10 times. Sorry, we are solving a system with a number of unknowns that is 2048 more than that we are solving on one GPU, by using a time that is only 10 times more than using one GPU. We are solving a system with more than 10 million of unknown in only 3 seconds, having a significant speed up with respect to the solution on CPU cores, and having not only savings in solve time, but also in energy consumption. Okay, if I have time, I can present rapidly some results obtained by using the library Honalia. Julia, let me know if...
Yes. Of course, Pasqua, please, you can take 10 minutes to present some results with Alia.
Okay. I like to present also some results obtained by using our libraries as integrated into a multi-physics code developed at the Barcelona Supercomputing Center. The ALIA code is used by our colleagues, in particular by Herbert Owen, in order to do some wind simulation on complex terrain. We test our precondition in large eddy simulation of a turbulent wind flow, which generated around the Bollen Hill in Denmark. This is an official benchmark for this type of problem. And the numerical model leads to a Poisson type equation for the pressure field. And we did some strong scalability tests for different mesh sizes on increasing number of parallel cores. We analyzed the strong scalability of our solvers, solving systems after a preprocessing phase in order to consider a fully developed flow and consider the total number of iterations and time to solve for 20 consecutive time steps. Let me know that in these three different configurations of meshes and of number of processes, we are using different time steps due to stability constraints of the velocity solver, which is explicit. We compare our PSBLAS based conjugate gradient coupled with the algebraic multigrid preconditioner, which I just discussed before, with the deflated version of the conjugate gradient method that is the native solver in ALIA. For our preconditioner, we use the same algorithmic parameters that I presented before, except for the case of the hybrid Gauss-Seidel, where we are using now 4 sweeps of hybrid Gauss-Seidel as a pre and post smoother. We ran this experiment only using MPI-based support of the libraries on CPU cores on Mare Nostrum. That is the supercomputer operated by Barcelona Supercomputing Center. If we look at the number of iterations, we can see that the yellow line that corresponds to the native ALIA solver is very high with respect to our preconditioner. Indeed, for all the mesh sizes, algebraic multigrid reducing a large way number of iterations needed by the solver. Here we ask for a 3 digits of accuracy in the solution of the linear system at each time steps and use the previous time step pressure value as a starting point at each new linear solve. What we can observe is also that the matching based precondition, that is the red line, show a large reduction in the number of iterations in the case of medium and largest mesh size. If we look at the parallel performance, we see that the time per linear iteration, which we have in these pictures, decreases for increasing the number of cores for all the 3 configurations of number of cores and unknowns. As expected, the original deflated conjugate gradient methods for ease one level nature has a smaller cost per iteration with respect to our algebraic multigrid based preconditional conjugate gradient iteration. On the other hand, the gain in the number of iterations permits to the multigrid methods to have the best time to solution with respect to the ALIA. This is the best time, this is the total time in solve phase. And we see that our multi-grid preconditioner win in all the 3 mesh side space. We also observe that multi-grid based on matching has smaller times, generally when the medium size is considered. We are trying to increase mesh size in order to solve problems with more than 10 billion of unknowns. And the difficulties are essentially related to the use of more parallel cores on the available infrastructure into P-rays. Let me go to some remarks and conclusion on this work. PSC Toolkit is a new software framework addressing scalability, flexibility, and robustness for high-performance scientific computing at extreme scale. The new parallel coarsening algorithm we developed in the EoCoE project using conjunction with the smoother prolongators and highly parallel smoother gave very nice results in terms of algorithmic and implementation scalability. Until now, we solved the systems with size larger than 10 billion on unknowns on the available pre-exascale supercomputers, embedding a hybrid CPU and GPU, NVIDIA GPU nodes in a very small time. And scalability results and comparison with software that are considered the state-of-the-art packages and developed in the USA laboratory demonstrates the validity of our approaches, both in terms of algorithms and in terms of software development. And integration and testing within very large scale wind simulation, but also within hydrology applications in collaboration with the Barcelona Supercomputing Center and Jülich Supercomputing Center demonstrated large benefits. Here I give some essential bibliography related to our recent achievements. And I thank you for the attention. I am happy to answer possible questions. Thank you so much.
Thank you very much, Pasqua. Just taking a look if there's any question at this stage. Anyone? Okay, if there's no question so far, first of all, thank you for this very interesting and real deep dive presentation. What I suggested that we take a 10-minute break and we reconvene at 11:20 for the last session of the day, which will be hosted by Fabio Durastante, and the conclusion of the EoCoE School. Thank you all. I'll leave the session open and we'll all be back in 10 minutes.
Thank you. Bye.
All right, welcome back. Fabio, are you ready?
Yes, let me share my screen. Okay.
This works fine. We can see it. You can go
Okay,
right ahead.
Okay, thank you. Okay, so now that you have a general idea on how the two main libraries work, to Salvatore's and Pasqua introductions, what I want to do with you is try a bit the code and specifically use the SAS portal to run some experiment. So let me try and start by describing you a bit of the code of the test that we will run. So as both Salvatore and Pasqua mentioned, the general form of a PSC Toolkit program is divided into substantially two parts. First of all, you have to use the routines from PSBLAS to create the parallel environment, allocate instantiate data, and specifically then you have to build your linear system and your right-hand side. For example, this is one of the test cases that you'll find in the library and that is installed also on the SAS portal. And what does it do? It generates the discretization of advection diffusion reaction type of boundary value problem in 2 or 3 dimensions by using finite differences. So this subroutine here takes as input the context, the sides of the problem you want to discretize, the various functional coefficients you see appear, and generates the linear system and the relevant right-hand side. So let's say that somehow we have implemented and reached this part. Then what is the next part? Well, the next part is that to solve our linear system, we surely need to couple one Krylov method with a suitable preconditioner. So this can be done by using an MAG express type where X can be S for real single precision, D for real double precision, C for complex, and Z for complex double. Then when you have instantiated this object, this is an opaque object, so you access it only through the AMG4PSBLAS routine, so you can set up the options needed to make it work in an object-oriented way. So what does it mean? Well, this means that first of all, you have to initialize it. And for example, if you want to initialize a multi-level multi-grid preconditioner, you just call on the variable p you have instantiated the function init on the parallel context you have selected, and with the string that tells it that you want to build a multi-grid preconditioner. If you just do this and nothing else, everything inside the preconditioner will be put to the default of the library. And in general, you can take a look at the documentation to see what these defaults are, but I'm going to show you to them in a second. Pay attention that in a way to be compliant with how Fortran works, it doesn't matter if you write down any of the string in uppercase or lowercase. They will all be converted to the uppercase and done the proper comparison inside. So it's not, the writing of the tags is not case sensitive. Okay, then let's say that we want to reproduce one of the preconditioner that Pasqua showed you in our presentation. So we want to set up the various part, and we can do it by calling again on the variable p the set function that has a certain number of strings and of options that permits you to set pretty much everything inside the preconditioner. Take care that in general you can, in a multi-level algorithm, you can select in principle different type, for example, of smoothers at each level, and if you use the set function correctly, you can achieve this and produce any preconditioner that makes sense for your application. As you see, this function and also the one before takes also this info variable. This is a variable of integer type that you can compare against one of the constant available in the library, that is PSB success. Salvatore told you this morning, but this PSB, whenever you see a variable that has PSB underscore something underscore, then this is a numerical constant, so you can use it to do a comparison with the result of the info variable. And then if info was not PSB success, then you can also push an error to the library, then to give you some informative answer on what has gone wrong in your routine. Then, after you have set all the options you were interested in, you can call the toBuild step for your multi-bit method, that are the hierarchy build and the smoothers build. The hierarchy build will, as the name suggests, will build all the sequence of smaller matrices from the finer level to the coarser one, while the smoothers build will perform all the build steps needed to work with a given preconditioner. For example, if you think that you're using a block EoCoE preconditioner with an approximate inverse on the block, when you call smoothers build, what will happen is that, taking the matrix on the hierarchies, you will build all the block diagonal matrices and then call the build phase of the approximate inverse on each block. So that in the end you end up with something that you can apply. Pay attention that sometimes, for example, if you are thinking of working in a Newton environment, for example, or in an environment in which you do time stepping, you may want to reuse the same hierarchy and to just rebuild the smoothers, since this is usually the hardest part to compute in your code. So maybe it's better to just rebuild the smoother and avoid doing, for example, again the matching from scratch for a matrix that is just slightly different from the previous one. After this procedure has been completed, then you can just call the Krylov method from PSBLAS, that is denoted by a string that contains the name, the matrix, the preconditioner object P, the right-hand side, and the value that will contain the solution on exit, that, as you see in this first three lines, we have put to 0. If you are dealing with, for example, a time-evolving problem, then maybe instead of having it being 0 in the beginning, you want it you want it to be the last time step you were working with. So it could be a good choice to, instead of doing this, pass to it the solution from the previous time step, or similarly in the case of a Newton method, maybe you just want to use the previous solution as a starting point. Then there are the classical information regarding the Krylov methods. So how many iterations, if it is a method with restart, what to do with restart, the tolerance on the error. And then you can also ask it how, if it has to plot something on the output in how many iterations. So for example, if you put it here 1, it will plot 1 line of output for each iteration, and stop deals with what form of the stopping criterion you're using. You can look at it into the guide. Usually 2, that is the choice using the relative residual, is the one that makes the most sense, but in general you may also implement other variants of this. Okay, so now we can try to run one example of this type on the SAS portal, but before, let me show you what you see in the code after you have installed. So let's say that you have installed your library somewhere in your system. At a certain point, you will find a directory called samples. There will be several subdirectories in it, and the examples that are on the SAS portal are contained in the simple directory, and specifically in the PDA gen subdirectory. So you see several files, and the one I'm going to work here is the AMG, the example ml.f90. So let me show you what is written inside of it. Okay, so you'll see, okay, the general disclaimer about the license, then some information describing what are the examples in here, but I'm going to come back to this in a minute. So let's look a bit to the code. So the code will use some modules from the library, so PSB base, PSB Krylov, PSB util, that contains all the linear algebra stuff, the Krylov methods, some utilities needed to work with input and output, and main module you'll need to use preconditioner for AMG4PSBLAS, that is MG Prech mode. Then these last 2 modules contains some part of the test case that were put inside modules to not clutter the code. So the data input treats the subroutines to read and print inputs from a command file, while MGDPDA mode contains the discretization routine for the finite difference problem. So you see the instantiation of the variables I've already shown you into the slides. So this is exactly the same code you have seen. We are fixing the format type for our sparse matrices to be CSR, but in principle you can pass this from you can pass it in at execution time, and then the code will do on the fly the format is most suited to the application you have in mind. And since we are going to solve the Poisson equation, then we are also fixing the Krylov method to be the flexible conjugate gradient. So, okay. This function is what is contained inside the data modules that does the read of input of parameters from file. Then you call the function I've shown you in the slide that generates matrices on right hand side. You get out some information of the times needed to create the matrix. Then you just need to select the preconditioner you want. And there are the example as three hard-coded preconditioner that I'm going to describe to you in a few slides. Then you call the toolbuild command, measures the times you need. This is the classical example of a call to the error function. So, for example, you check that after the build phase, the two build phases, you have succeeded, and if this is not the case, you push out an error in which you tell to the user that there has been an error in name, that is the name of the function, that is hard-coded in the variable at the beginning, and you get this string to help you decode what has gone wrong. Then there are the few lines of code that permits you to put 0, the initial guess for the Krylov method, and then call the flexible GG on the problem. Then we do a by-hand computation of the final residual. Since I don't know how well versed you are in the Krylov stuff, but if you're using the flexible GG, then the residual you are computing is computed by using recurrence relation inside the Krylov space. And there may be a bit of cancellation and in this procedure. So at the end, it could be a good idea to also check that the proper residual is what you expect it to be. And as you see, this is all obtained by using BLAS-like operation with the routines that are implemented in PSBLAS. Another useful function is this size off that permits you to get information on the size of the objects you have built. So this can help you to estimate how much memory you need on on some small examples, and give you a bit of granular control on what you're doing. Then at the end, we just print out all the various information, and then free everything, and the code concludes, as Salvatore already told you, with a PSB exit on the context that terminates the parallel environment. And substantially, that's the main part. That's the main part of the code. So I think I had already compiled it, right? So if you want then to run it on a machine that you have, then you can just do, for example, a certain number of processes. And this will print out something. Now we're gonna discuss the output after you have tried running it for yourself. And furthermore, if you also want to look at the input file, this contains substantially four values that are the choice of the preconditioner, the size of the domain, the maximum number of iteration, and the tolerance for the Krylov method. So you can pass it to the code, as I have done just by putting the name of the file in the standard input. Okay, so I don't want you to have the library installed and to run it on your machine, but let's see what we can achieve with the SAS portal. So the first step is logging into the portal. So you should have your account for this. So this is the portal. You push the login button and then do the login. I did it with and you end up on this page. Then the second part is how do we select the example we actually want to run. We can do it from the templates button up here. Then we see several templates of codes we can run on the machine. And we are interested in running the example using AMG4PSBLAS. So we select it, then it appears on the right, and then we can select submit a job with this template, and we end up on this mask. So if you select from here AMG the example ML, you just open. You are working with the file I've shown you before. So this exactly corresponds to this test file here. And then you have the four options that are exactly the one that were into the input file. Okay, so let's say that we want to use the first preconditioner choice. We set the domain size to be 100, the maximum number of iteration to be 500. We hope that they will be far less than this number. And then the tolerance to the solution, that if I can count the number of zero, is something like 10 to the minus 6. Then what are the preconditioners that are implemented in there? You have the two-name algebraic multigrid preconditioner Pasqua showed you, so the one in which the aggregation phase is done by the Vanek, Mandel, and Berzina algorithm, and in a parallel decoupled way, and the one based on the matching of the graph that is this is again parallel and coupled. And if you look at the other example files from here, so from is instead of this one, you select the one that is called OneLev, then you also have the possibility of running one level preconditioner that, as the name suggests, is an additive Schwarz. So to build the precondition, to build algebraic multigrid, you have to set up all the various bits and pieces. So smoothers that can be possibly different at each level. One of the two coarsening strategies. Are you going to use them in a smoothed or unsmoothed way? So you are going to do an iteration of Jacobi on the tentative prolongator or not? And what type of courses solver do you want to use? A direct solver, this replicated solver, and other iterative methods like the one you were using in Smoother, or maybe an external library in between the one we support. Then you also have to select what type of cycle you want to use. So either a V cycle, a W cycle, or a K-cycle. Please pay attention that if you are going to use K-cycle, then you are forced to use the flexible CG because the preconditioner is now non-linear. So you have to build the Krylov subspace in what is no more a Krylov subspace, but the right projection subspace in a meaningful way. So, okay, let's see. As I've shown in the code, all of this code can be done by call to the pset function. So these are the options. So we are going to start by trying the preconditioner choice 1, and this is substantially the default. And what is the default? Well, the default is a V-cycle with smoothed decoupled Vanek bundle Brezina aggregation, and using one hybrid for backward Gauss-Seidel iteration for pre and post smoother at each level. And as course solver, we either use UMF pack from the Sweet Sparse library if you have it installed and if you have made the library aware of the fact that you have it, or if this is not installed, to be able of running even without asking the user to install anything, then you convert to an incomplete LU factorization with 0 level of fill that, for example, in the case of an M matrix, you're sure produces irregular splitting, so it's a meaningful fixed point iteration. In general case, you don't know, but if you really don't know, maybe then you have to install something else, or do another thing that I'm going to show you next. Okay, let's say that we have fixed all these choices. Then the next thing we have to do is set up the resources. So this is a Poisson problem of 100 to the third power, so it's not too large. So the duration of our job will be surely less than an hour. And for example, we can try to run it on 6 core just to look at what happens. In the output file, permits you to decide where the output and the error stream go, or if you need a directory, I would suggest to leave everything in place. Okay, now that we have selected everything, we can just click the submit button, and then you get this mask that tells you that the job has been submitted, and we can look at the state. So it has been pending for a few seconds, and now it's executing. So it's in the completing phase. We can refresh the output from the mask on top, and if things had gone well, you see that in the end you get a finished check here. So we can look now at the output file by clicking on these two buttons. For example, let's look at the output stream. It will load for a bit, okay, and then you'll see pretty much the same thing I was showing you from the shell before. So let's try to look a bit into the result. Well, in the top, the first information you get is the welcome message that tells you that you're using the MG for an example from MG4PSBLAS, the name of the example, the size of the matrix you are trying to generate, the format you are using, And then you also have the information regarding how much time do you need to allocate, generate the coefficient, assembly the descriptor, assembly the matrix, and the total building time. Okay, so this is a first type of measures that tells you how efficient the build phase is. Then you see the things you are most interested with, probably, that is the convergence history of your creel of methods, and you see that for this test problem and that preconditioner in 10 iteration, you reach an error estimate that is below the tolerance we have set. So we have reached convergence in 10 iteration. Then there is a bit of a mouthful of information, but these are needed to understand what you are actually doing. So it prints out the description of the preconditioner. It tells you that you're using a multi-level preconditioner in which you do just sweep of whatever cycle it will be. Then you have information on the pre and post smoother. So you're using an hybrid forward Gauss-Seidel here and an hybrid backward Gauss-Seidel as post smoother. So we are solving a symmetric positive definite system, and we want our multi-grid methods to be symmetric as well. So we select on one side the lower triangular part to build Gauss-Seidel, on the other side the upper triangular, so that when we do the transpose of the whole matrix, we get something that is symmetric. Then you get an information regarding the number of levels that have been built, the operator complexity, so the number of non-zero of the various coarse matrices summed up and then divided by the number of non-zero of the fine matrix. This is a measure of how weighty your hierarchy is. The average coarsening, the information of the type of cycle, how many smoother sweep you do, then the information on the type of aggregation you're using, so a decoupled aggregator that uses the strength of connection measure, that is the one from the paper by Banek, Mandel, and Brezina. The fact that you're using it in a smoothed way, so if you're a bit familiar with the paper, for this strength of connection in algebraic multigrid, you are pretty much forced to use the smoothed one. Then an option on filtering, so if you see that your operator complexity is going too high, you can put a filtering options that will automatically drop some of the entries of the coarse matrices to make sure that your preconditioner doesn't become too big to handle, and then some information on how the smoothing has been done. So we have done the smoothing of the prolongator by using the EoCoE method with a weighted EoCoE method, where omega is an estimate of the spectral radius, and this estimate has been done by using the infinity norm. This is the formula for the operator complexity I was mentioning a few seconds ago. Then you have the information in a level-by-level fashion. So you get what the actual value of the damping are, what's the aggregation threshold for the strength of connection, and then you get information on the global size of the matrix at that level, what are the non-zeros, the sizes of the matrix on the various block, and what is the aggregation ratio. This substantially tells you how many doves have you aggregated in a single coarse variable. And you edit the same information for all the levels, Then on the fourth one, you see something that is slightly different. And because this is the course level, and on this one, since we have put the default, we would have expected to have UMF-Pack from Sparse Solver, but this is not installed on the portal. So we default to the inner default, and we do an incomplete LU factorization with 0 level of fields in a replicated setting. This means that the course matrix is replicated as is in all the processes. Clearly, this is not the best choice for this kind of scalability that Pasqua showed you at the end of her talk, but for such a small problem, it's still doable. So what you can do now is trying to repeat the same example with the other two preconditioner. The second one is again the default one, but we now do something different for the smoothers. So we use, instead of hybrid forward-backward Gauss-Seidel method, we combine block Jacobi with a course subsolver that is an ILU factorization, and we do 8 sweeps of it. Now this is a distributed course solver, so it will hopefully scale better than the one in which we were replicating everything on each core. Finally, you can also run one of the preconditioner that were in the previous presentation, so the one based on the matching strategy. So you start again from initting the ML, then you tell it that you're using as an aggregation algorithm something that is a coupled aggregator, and amongst the coupled aggregator, the matchbox P. So this may seem like a bit of an overkill at the moment because we just have one coupled aggregator, this is matchbox P, in the current version of the library, but we are developing other ones. So at a certain point, the fact that you have to do 2 calls will make more sense. Then you can try to select the sides of the aggregate for the matching, so you know that you will have aggregates that have at most sides 8. Then what type of cycle? For example, let's do a W cycle. Let's do 2 smoother sweep. And now let's try another course solver that is again distributed. That is another Krylov method. So we are using it in a distributed way. So we are solving the course matrix with another Krylov method. And what Krylov method? Again, the flexible CG. Okay, so you can try to run this by doing again, I can no longer cancel the task, okay, by doing again the whole procedure, and for example selecting here, okay, let me show you the one with the matching. So selecting 3, selecting 6 cores, and then submitting it. Okay, now it has been submitted and it will take some time. The last information that you can gather from the examples are related to the number of processes you run, the system size, the of methods, and all the involved timings and residuals. So together with the total memory of occupation for A, for its descriptor, and the memory that has been occupied by the preconditioner. So in the, I know it's not much time, but in the time we have left, what you can try to do is to replicate some of the graph that Pasqua showed you regarding strong and weak scaling by using the resources in the portal. So, for example, you can try to do the following: fix largish size of problem that you want to solve, and then try to launch scripts by using every time doubling the number of processes, and try to see if you can look at how for example, the computing time is behaving, or how many iterations you are actually employing, or maybe it was also worthwhile to look at the operator complexity per number of processes. You can use those data easily also to compute both speed-up factor and parallel efficiencies. For example, if in the strong scaling case, you take the time needed to run on a processor or on the number of processors that is your baseline, and then divide it by the time needed to run on NP processors for larger and larger number of processors. This gives you your speed up factor. And if you divide it again by the number of processes, then you get your parallel efficiency. So if the code was embarrassingly parallel, you would expect something like an efficiency of 100%. This will not be the case. If you try it, you'll see that depending on what preconditioner you're using, this value will be lower, but fortunately not too much, because as you have seen in the through experiments in Pasqua's lectures, the code actually works on realistic case. You can do something similar also in the weak scaling case. So what's the idea of weak scaling? So you vary together both the number of processors and the size of the problem on each processor, and you make them grow. Both at the same time. So while the strong scaling was a measure of saying, okay, I have a very big problem, and I want to know that if I use more resources, my solution procedure will improve. The weak scaling is on the other side, tackling the problem on while saying, okay, this is the biggest problem I can solve, or somewhat the biggest problem I can solve on one process. Let's see if, with some performances, let's see how performances behave when I try to solve a problem that is double the size in double the number of computing units, or triple the size in triple the times of computing units, and so on. So for this case, the speed up can no longer be computed this way, but you can compute directly the efficiency by comparing the time needed to work with one processing element and dividing it by the timing needed by solving the problem that is NP times bigger on NP computing unit. So let's see if the other code has ended. Okay, so it has finished. So we should be able of looking at the results. Okay, in the standard output stream, just to show you the differences. So first of all, thing we are quite happy about, actually using the coupled matching improves the convergence of the problem. So we had gone from 10 to 5 iteration. The operator complexity is a bit higher, but the average coarsening is quite near 8. So this means that we are practically obtained what we were asking. So we are practically obtaining aggregates of size 8 consistently. We do one level more, and as you see, we are using the Krylov solver as course solver. Then you can also compare the other information. So okay, so I would like for you to give a bit of a try to this in the portal, and I'm clearly here available to answer any question, or even if somebody wants to share his screen and showing us what he or she is doing.
Thank you, Fabio. We received a question from Redouane, who asked that he received an error for 400 when he submitted his test. Do we have an explanation of what such an error could mean?
So you try, okay, let me see if I can open somewhere the chat. Here. Error code on the portal. So it's an error, an error code on the HTML, or it's an error code inside the...
I think it's an error code linked to the portal after he submitted his job. The issue that I don't know what the technical specification of this specific error code.
Can you let him share the screen, maybe?
Of course. Redouane, if you want to share your screen to show what happens and why you have this error, please feel free to do so.
So I think it's possibly the best way to do debugging.
Yeah. Okay, he doesn't seem to want to do so. Pavel, do we know what the error code 400 means?
Well, I don't know if I can look there. Okay.
Okay. Thank you.
Oh, this error, because I'm not sure now. Okay.
Okay, so this seems like something on the portal.
Yeah, request failed with status code 400. This seems to be a technical issue with the portal itself. Fabio, the input codes and numbers that Redouane used seem to be correct, right?
Yeah, right. Let me look also at resources just to see. Can you put the mask on the resources on top?
Yeah, the resources. Yeah.
Okay, so you are using just one core, so yeah, it should be doable.
Okay, Julian, you are not mapped to an account on Eagle, so wait a minute, I will map you.
Oh, okay. So it's because you hadn't been registered with an account, so that's why the portal didn't let you send the job.
Okay, so it was easier. Okay.
Okay, thanks.
But I can't see your account on portal. What email you used?
Give me a second. That should be okay. I'm sending you the email right away. Check.
Okay, then if there is somebody else that is trying.
Okay, Ridwan just send you the email. Okay, sorry, he sent it to me. Pavel, I'm sending you his email right away. There you go.
Otherwise, I don't know if there are other questions, or also maybe for I see that Pasco and Salvatore are still connected. So if you have general curiosities or want to talk about something while playing around, this is a good moment to discuss.
Absolutely.
I want it to be an end song, so.
Okay, well, in this case, just to conclude on Ridwan's issue, so Pavel is adding your email to the list of contacts who have an account on the SAS portal, so that should solve the error code you received when trying to submit your jobs. I don't know if there's any other question from anyone at this point.
Yeah. Or also if you want to tell us what are the application you're working on, or if you are just to get a bit of a feeling of interaction, also for us to know what you're interested in. It's just open your mic, or even if you want your webcam. Maybe I think that Julian can avoid putting your faces and on YouTube channel at the end.
No, I'm not going to savagely open people's mic and camera just if they don't want to. I can tell you that Amel Galuji, he's one of our PhD students here at CA, and she works with Julien Bigot on the PDI interface.
Okay.
And she was also there on day one. Couldn't join yesterday because she was teaching. So that's it done for her. And for the assistant, I know that Mr. Sheliga has been following us yesterday as well. And he wants to say a word regarding what he's working on. Nah, doesn't seem like it. Okay,
okay, I tried.
Mr. Bouchouibat, Ridwan, if you want to say a word on where you're from and what you're working on, so we have a bit of feedback on our participants.
Hello, everyone. Do you hear me?
Yes.
Yes. Okay. I am Ridwan Bouchouibat. I work in Mohammed VI University Polytechnic in Morocco, Marrakesh. I am interested in HPC domain. Also, my background is applied mathematics, and I am interested also in preconditioner and all think about HPC, parallel tools, and I manage a platform of HPC, so I have to bring new tools for our users, and so I am here.
Okay.
Okay. If you want to install all our libraries, clearly they are free to use, so feel free to do so. And even if you have questions, don't refrain from asking.
Yeah, but our users are interested also in Python language. So my question is there any API for this preconditioner with the Python? just to make.
So no, at the moment we just have interfaces for C and Fortran. So Python was a bit out of our focus, but honestly, I don't think maybe Salvatore is the best person to to have an idea on this, how difficult it is to interface this stuff with Python.
That's something I didn't look at closely. I would need to find somebody to. First of all, we need to look at the MPI interface for Python to see how to interact with that one. But I suppose that through the C interface, we could write Python wrappers for that. Other than that, I don't have a clear idea because I haven't had too much experience in doing that sort of thing. Sorry.
Okay. Well, thank you all. Ridwan, just so you know, Pavel just entered a message saying that your account on the SAS portal has been created. So if you want to submit your job again, you should be able to do so.
Okay, thank you.
Thank you.
All right. Well, this is going to conclude these 3-day schools. So once again, I would like to extend a warm thank you to our hosts and researchers for your availability, for the depth of the tutorials we've been giving us. All the sessions have been recorded, so I will upload them on EoCoE's YouTube channel and make sure to give them the relevant promotion they deserve, because these were really interesting days, and I hope that we'll get people to take a look at them. I'd also like to thank the participants, of course. Some of you have been following us for these 3 days, so thank you very much for your attendance. Really appreciate it. As was mentioned, we have noted those of you who joined us and followed the days and were active, more or less. And we will come back to you on an individual basis to discuss the possibility of extending a few prizes for your participation. I'm answering a question in the chat. Will the SAS portal be available for more time? Yes, absolutely. Pavel, correct me if I'm wrong, but the SAS portal is meant as an open tool. So if you have an account on it, you should be able to keep submitting jobs and play with it, right?
Yes, the accounts that are configured now for the summer school are active up to Friday. If you need more time, please email me and I will set up it for a longer time. But it is on request. I will put my email in the chat.
So account up until Friday, and if you want to keep taking a look at what the SAS portal can do, please let us know about it. Just contact one of us to make sure that Pavel has the information to extend your account. So, all right, so this concludes the school. We'll come back to the participants with the question of the rewards for your attendance. Thank you to everyone. And for those of you who are part of the project, we'll be happy to see you in Naples at the end of the month for the final consultation meeting of the project. And if anyone has something they want to add, now's the time. If not, well, let this conclude the school. Thank you all and have a great day.
Thank you.
Thank you, Julian. Thank you, everyone.
Thank you.
Bye.
Thank you.
Bye.
Bye, everyone.
Bye.
Take care.
Bye.